Hello, my name is Will, and I'm talking to you today about big things, small things, and everything in between. Which is a very general sort of topic, but basically I'm going to be showing you how physics and science in general, they can explain the same things that happen on a really small level, and things that happen on a really big level, using basically the same ideas. And that's sort of how we know when we've got a piece of physics, like we understand it really well, because we can describe things no matter how big or small they are. So we can use things that work like down as an ant collecting food from a leaf or something. Same ways that we can describe that and describe kind of if some water hits him or something. We can then use those same descriptions to work on how, say, Jupiter, its clouds are swirling together or something, and obviously everything in between of that. So the first of I've got three things that I'm going to tell you about that kind of span all sorts of sizes. My first one is spinning. So we all know about things that spin. If you've been on a roundabout in a playground, if you watch water going down a plug hole, got a nice picture of that here. We've got bacteria that, there's millions and millions of them that you could fit on a pin. They have little spinning motors in them that let them propel themselves along through water. The big red spot on Jupiter is you could fit about 3 Earths across that image. It's massive, and like a colossal hurricane running in Jupiter's atmosphere. And obviously we have real hurricanes on Earth, and we have tornadoes. And tornadoes are what I'm going to sort of go on to describe a bit more here. Which brings me on to my first demonstration. Here, I've got a spinning turntable. You'll see, yep. Oh, I'm going to drop the lights a little bit. Maybe. Technology doesn't like me today. So here I've got some barbecue gel, which you use to light barbecue, and which burns. So I'm going to put that onto this. And then I'm going to set fire to it, because, fire is always good. Right, so as that gets going, I'm going to explain what's going to happen. The fire, because the fire is hot, it tends to rise upwards. So if when you hold a match or you've got flame coming off it, that fire tends to go upwards. So air is going to come in the bottom of this flame and upwards through it. So then on top of that, on this, partially to keep the flames away from me, I'm going to put a big metal cage. Okay? But as air gets drawn into the bottom of this fire, if this metal cage is spinning, then it's going to start the air spinning as well. Like if you're trying to run through a revolving door, you're going to start spinning, go around with the revolving door. So if I start spinning this, then air is going to come in here and up the middle. And as it comes to here, it's going to start spinning. But if you ever tried, going into the middle of a roundabout, or watched a ballerina, who starts as they're spinning, or an ice skater, who starts as they're spinning with their arms outwards, and then brings their arms in, and that makes them spin faster. So as the air comes in here, it goes from the outside to the inside, and that makes it spin quicker. So if I start spinning this now, then that air, as it comes into the flame, gets the flame to start spinning with it. And the air comes in the bottom and comes up the middle, and as it goes, the flame spins. If I let it slow down, then because there's friction in the plate and there's friction in the air, then that means that the flame stops spinning and it just goes back to being normal and low. But if I keep it spinning, then I can get a properly nice flame going up. Okay? And it goes out. So this isn't just a thing that we can have in a laboratory. Okay, so here I'm showing you where the airflow is going. But these are also things that happen in the real world. So if a tornado hits a bushfire, where kind of lots of the ground is burning, like the bushes are all on fire, or sometimes these form not like normal tornadoes, but just because of the hot air coming up from the fire, then we can get these really, really impressive flames shooting upwards. I've also got a video which, given my current luck with technology, I don't think I'm going to risk. But if you could just Google flame tornado, you get amazing sort of things shooting up that look like this. And they're really dangerous for like firefighters and people trying to fight bushfires, because they can kind of get sucked up and things. So that's how things spin, and they keep spinning. Now, second one, feedback. So normally when we talk about feedback as an everyday thing, it's like you fill out a feedback form. So you go to watch a lecture and you think, I really wanted more explosions. So you fill out on the form, I think there should have been more explosions. Next time I do a talk, I put more explosions in them. But then maybe we got to too many explosions. Maybe there were small children getting very upset and starting crying because they had so many explosions. Then people fill out a form going, you just blew everything up, I couldn't see anything. At which point I bring down the number of explosions I have until I find the kind of right point. And if I start moving away from that, I get corrected. So the first example that we have is bacteria. Bacteria, they aren't really that good at moving through stuff. They move for a bit, and then they see what it's like. And if there's enough food and things, then they'll slow down, they won't move as much. But if there isn't enough food, then they keep moving. And so they make sure that they're in a place with the right amount of food by kind of sensing how much food is in their environment, and if there's enough, staying, and if there's not, moving on. And so they stay at the right level. We've also got two more examples. The first one is the sun, or indeed any other star, or most other stars. So if the sun stops burning so efficiently, it gets a bit colder, then we're down here where the sun gets cold. But as it gets cold, because it hasn't got as much energy, and the energy pushing out is what keeps it at its size, then it starts shrinking. But then as it starts shrinking, all that heat that it had gets more concentrated down, and its reactions that keep it burning start happening quicker and quicker and quicker. And as they start happening quicker and quicker and quicker, they make more energy, and that energy is what's pushing it out again. So it gets energy, heats it up, gets hot. Once it gets hot, it gets bigger again. But now it's a bit big. And as it spreads out, its heat that isn't as close together, there's not as much of it, so it cools down again. And then it kind of averages out over time until it gets back to its temperature that it wanted to be at originally, and about the same size as it was. Another example is when we have predators and prey. So if suddenly it's a bumpy year for cheetahs. All the cheetahs have kids, and loads of cheetahs. Then suddenly, the gazelle that the cheetahs eat, those cheetahs, because they keep eating all the gazelle, there's very, very few gazelle left. But if a cheetah's in a place where there aren't very many gazelle, he's going to go somewhere else. Because they're really, like the ones who are left, they're going to be the strong ones, the quick ones that are really hard for a cheetah to catch. So all the cheetahs leave, and like maybe one is left on his own. But then, if there's only one cheetah left on his own, then the gazelle, they can have lots of kids, and they can move into the area because they're not going to get eaten. There's only one cheetah, and he's not got a very big stomach. But then, if we got lots of gazelle, all the cheetahs are going to move back. And so this goes round and round, and as we go, we get to a point where there's the right number of cheetahs that the cheetahs are eating the gazelle, but not so quickly that the gazelle can't make more gazelles. Okay, so to demonstrate feedback, I'm going to balance a stick. Here, it's the biggest one I can find. I'm sorry, it's larger. So if I try balancing a stick on my finger normally, and if I leave go with my left hand, what's going to happen? Yell. It's going to fall over. Yeah. But if I use a feedback mechanism or way of doing things, so if I look at the top of this stick, then as I see the stick starting to fall, that picture goes to my brain, and my brain says, move your finger to the side. And so I move my finger, and then the stick starts falling in a different direction. But if I look down, then I break the loop. Then I can't see it, and if I can't see it, I can't move my finger right. And so it falls down. So I can do it, I'm looking up there, I look down at you, it starts falling. Okay? And you can do this at home as well. It's slightly more difficult with a smaller stick. But if you get like a 30cm ruler, like the ones you probably use at school, or some form of, I've got a magic wand at home that's really quite good for it. Gold, shiny, got a star in it. That's not necessary. And then if you keep your eye on the top, like looking halfway down is okay, but it's not good, because the top's the bit that moves the most. And so I look at that, and then that tells me where to move my finger, and so I can keep it up, even though that's not a natural place for a stick to be. Oops. Right. So, my final thing, which is kind of what goes, another thing that applies to every sort of thing, are capacitors. So, some of you probably don't know what the word means. I'll explain in a second. But capacitors, you find in camera flashes, all sorts of them in computers and things, and also in lightning storms. So, a capacitor. We get, there's two types of materials. There's conductors and insulators. A conductor lets electricity flow through it. Electricity is where electrons are moving. Yeah? So we get two sheets of conductor, like a metal or something, and then in between them we're going to put a piece of insulator. So insulator, electrons can't go through, electricity can't flow through it. So instead, the electrons have to stay in the pieces of metal. Then, to that sort of sandwich, like insulator sandwich, don't eat them, we're going to attach a battery. So batteries have got energy in them, and with that energy, we're going to move electrons as electricity from one side of the conductor to the other. So, slightly confusingly, that means that we move them from the side that's got the pluses on to the side that's got the minuses on, because electrons we count as being minus. And so we're going to attach a power source, like a battery, over that, like to either side, and we're going to move electrons from one side to the other. So moving electrons from one side of the capacitor to another, we put energy into it. So it's like if we get a hill, and we all got like some big balls and rolled them up the hill, then that's equivalent of us having moved electrons from one side of this to the other. If we then let go of the balls, as we've got them to the top of a really big hill, what's going to happen to the balls? Yep. They're going to all roll down. So if we stop pushing with the battery, then they're going to roll down. They can't roll down immediately, because if we just take the battery away from here, then there's no way of them getting down, because there's an insulator in the way. And we just said that electrons can't go through an insulator. But then what we're going to attach is a light bulb. So all the electrons, as they go through the light bulb, are going to push, they can knock into bits of the light bulb as they go through, and that gives out light and some heat. And so when you have a camera flash, then we use the camera battery to charge up the capacitor. Charging up is where we push all the balls to the top of the hill, effectively. And then when we put the light bulb across, like to either side of the capacitor, instead of the battery, then suddenly all the electrons rush through the light bulb, and so we get a really bright flash of light. And they do that much quicker than they could do if they came out of the battery. So that's why we use the capacitor. So, another place where we get a capacitor sort of effect is in a thunderstorm. So we've got negative, which is what we said the electrons were, and that all happens at the bottom of here at the bottom of the thunderstorm. So that happens because ice crystals are moving upwards in the thunderstorm, and they tend to leave their electrons at the bottom as they go. But the important bit that we're worried about right now is the gap here, between the cloud and the ground. You do sometimes get effects because of this bit here, but most of what we see is here, because that's we're around here, but hopefully not outside, because you won't be outside in the lightning. So we've got, up here we have where the electrons are, and down here we have where the electrons want to be, back where there's not very many electrons. But we have a gap in between. That gap is like our insulator, it stops electricity getting through. So it just sits here, you have a bit of a rainstorm, but you don't get lightning. But eventually, there's so many electrons, they so want to be on the ground, that one of them or a couple will find a path downwards. And when they find that path, then that path becomes a really, really good path for lots of other electrons to come down as well. So, like having a light bulb, except all we've got is air, but air that we can get electricity down, then all the electrons come shooting downwards in lightning. So, obviously I can't make lightning in here, don't have any rain clouds for a start. But what I do have is a very large capacitor. So this might not look very large, but the ones that you tend to have you get some computers or in your camera flash, are about this big. So this has got about the same effect as like 1,000 of those capacitors. And if I attach my power supply here, and I'm going to put it up on the big screen so you can see as well. Thing here. Yes, excellent. No, that didn't go up on the big screen. Oh, technology. Once my glamorous assistant puts that on there, I'm going to explain. Here I've got basically a battery, but it's actually plugged into the mains, to the electricity coming from a power plant somewhere. And I'm going to use it. Yep, good. I'm going to put these two leads from it across this capacitor. So one on either side. So what I'm doing is the equivalent of pushing the balls up the hill. Like we said before. That's quite upsetting. Experiments are very, very prone to not working. But I don't know why. Okay. So what's going to happen, if I'm just going to get that working in a second whilst we're doing this, is that I'm going to put these one either side of here, and they're going to move the electrons all from one side to the other. But then, in the same way that, so those are going to be separated, they can't get between because we've got an insulator, we've got air in between. But then here, you can see, I've got some strands of wire. Is that working? Yes, it is. Yes, excellent. We've got an effect. Good. So, not my day for technology. Oh. More in a minute. So, put those across. This is going to charge up so that we now have lots of electrons separated in this. Like, all the electrons on one side and none of them on the other. And so if I now get a wire, I think that's 80 goggles, and so I'm going to close the gap between the two sides so that there's a conductor in the way and it can flow. But this time I don't have a light bulb in the way. So as the electrons come across, they go so quickly that all they've got to hit into them as they come across is bits of the wire. So they heat it up and bits of liquid metal, because it's melted it, are going to go flying across. Oh, well, that wasn't very good, was it? Right. Left light? Maybe, no. Not my day. I'm going to have to charge this up again. So, charge this up. So I'm going to move all the balls back up to the top, and then as I bring it down, it's got a bit of a delay on it there, but you can still see it happen. And I can keep doing that pretty much all day. There we go. I don't have to make this safe because people get annoyed with me if I start destroying things. There we go. So, what have we covered? We have covered spinning things from big massive bits like Jupiter, the other way, the red spot Jupiter like a hurricane, all the way down to plug hole sized things, particularly flame tornadoes, which are quite scary. We've covered feedback loops. We've covered how, if you look at what's coming out of the system, so whether or not the stick's falling, and we put that back into the system, in the form of moving my hand to keep the stick up, then we can keep the system at the same level, and it doesn't massively go away, it stays in the right place. And finally, we've looked at lightning, capacitors, and things that we get in everyday devices, but if you get a really big one, you can make some sparks. Thank you very much for listening. If you have any questions that you want to ask, feel free to come down to the front and ask me them in a minute. Otherwise, thank you for being such an amazing audience. Can you give yourselves a big round of applause?